All right, let's dive right in. We're looking at a new discovery today that is shaking the very foundations of cosmology. It seems that thanks to some truly mind-blowing evidence from our newest eye in the sky, our entire understanding of the universe, well, it might just be wrong.
So, this is the big question, isn't it? Our most powerful space telescope is finding things out there at the very beginning of time that, according to all our best theories, simply shouldn't exist. It's a genuine cosmic whodunit, and the clues are just now starting to come in.
To really understand this cosmic crime scene, we first need to meet our lead detective. And in this case, it's the most powerful one we have ever built.
I'm talking, of course, about the James Webb Space Telescope. You really have to think of JWST as a time machine. Its incredible mirrors are so powerful they can capture the faint, ancient light from the very first galaxies, as they were forming just a few 100 million years after the Big Bang. But the story it's telling us is not the one we expected. And that brings us to the central clue in this whole mystery, the baffling discovery that has cosmologists absolutely scrambling for answers. It turns out that JWST has found some, well, you could call them impossible babies. I mean, just look at the contrast here. It is dramatic. For decades, our standard model of the universe predicted this slow, gradual buildup. The first galaxies would be these small, wispy things that would take billions of years to grow. But JWST looked back and found the complete opposite. Huge, fully formed, massive galaxies, already shining brightly in the cosmic dawn. They are simply way too big, way too early. It's like finding a full-grown redwood tree in a seed tray. And we're not just talking about a tiny discrepancy here. See, astronomers measure cosmic distance and time with a value they call redshift. And these galaxies are being found at a redshift greater than 8. Now, what that means is we're looking at a time when the universe was in its absolute infancy, less than 650 million years after the Big Bang. According to our models, the universe simply shouldn't have had enough time to build anything this big, this fast.
So if the evidence doesn't fit the theory, what do? Well, maybe the theory itself, our fundamental recipe for the cosmos, is wrong.
For years, the reigning champion of cosmology has been this model right here, ΛCDM. It's our standard cosmic recipe, and it has been incredibly successful. I mean, it explains everything from the afterglow of the Big Bang to the large-scale web of galaxies we see today. It is the rulebook we've been using for how everything gets built. But here's the massive problem. Data from 2 huge JWST surveys, called CEERS and JADES, flat out contradicts this model. Under the rules of ΛCDM, there's just no physical way for matter to clump together fast enough to form these enormous galaxies so early. The standard recipe is failing its first major test in the early universe. Now, a crisis like this opens the door for some really bold new thinking, and one researcher, Marco Saba, has proposed a solution that is as elegant as it is radical. What if one of the fundamental rules of the universe isn't constant at all? This is the core of the new theory. Forget what you learned in physics class about g, the gravitational constant, being, well, constant. This idea suggests that in the early universe, the force of gravity was actually stronger than it is today, and it's been slowly weakening over cosmic time. And there's your solution, right there. If gravity had more pull in the beginning, it would have acted like a cosmic accelerator. It would have pulled gas and dark matter together way more efficiently, basically supercharging galaxy formation. And suddenly, those impossible galaxies aren't impossible at all. In fact, they're the natural results of a universe with a stronger early gravity. But a good idea is one thing. Matching the evidence is something else entirely. So how does this wild new theory of evolving gravity actually stack up against the cold, hard data? So here's the evidence straight from those JWST surveys. Each one of these black dots represents a real measurement of how many massive galaxies existed at these incredibly early times. This is the reality. This is the set of facts that any successful theory has to explain. Okay, now let's plot what our standard theory predicts. This blue line represents the prediction from that ΛCDM model. You can see it immediately. It falls way short. It predicts far, far fewer massive galaxies than what the JWST has actually found. It's not even close. But now watch what happens when we plot the prediction from the new evolving gravity model. That's this red line. It just threads the needle, passing right through the data points.
It predicts exactly the number of massive early galaxies that JWST is observing. The match is absolutely stunning.
And this isn't just about us eyeballing a chart. Scientists use powerful statistical tests to figure this out. And these tests actually penalize new theories for adding extra complexity. But even so, the evidence comes out strongly in favor of the evolving gravity model. It's just a much, much better explanation for what we're seeing.
Now, if this theory holds up, its implications go so much further than just explaining some big early galaxies. This could force us to rewrite some of the most fundamental rules of physics.
This theory could be a key that unlocks multiple doors. The same idea of evolving gravity might also resolve other huge puzzles in physics, from the problem of the Big Bang singularity and the mystery of dark energy, to maybe, just maybe, providing a path toward finally unifying gravity with quantum mechanics.
Of course, this investigation is far from over. JWST is continuing to push deeper into the cosmic dark, and a whole fleet of upcoming observatories, like the Roman Space Telescope and the Euclid mission, are going to test this idea with incredible precision, mapping out cosmic history to see if gravity's strength has indeed changed over time. As the author of the study concludes, this isn't just about tweaking a model. This is about potentially finding a whole new path toward the fundamental laws of our universe. It transforms the JWST's strange findings from a problem into a profound clue.
And that's the ultimate takeaway, isn't it? We tend to think of the laws of physics as these rigid, unchanging pillars. But what if they're not? What if gravity itself is part of the universe's evolving story? That is the powerful idea we're left with today.